Okay, welcome back, Physics 30s, to our next lesson in Chapter 5. This is 5.4, and today we're going to look at producing photons. Okay, so in the past two lessons, we were looking at the photoelectric effect, and that was describing how photons of a certain energy could knock electrons off of a metal or liberate them from that metal. And we said that those photons need to have a certain amount of energy. And we determined that a photon's energy is determined by its wavelength or frequency, as we can see by these two diagrams. The one with a longer wavelength or a lower frequency has less energy, and one with a shorter wavelength and a higher frequency has more energy. And we made the comparison of a ping pong ball to a bowling ball, and trying to knock an electron off was kind of like trying to break glass. And if the energy of your photons aren't high enough, doesn't matter how many you send, you're not going to knock any electrons off. But if you have just one photon of enough energy, it is going to knock an electron off, or in our analogy, break the glass. And now in this lesson, we are going to reverse it.
Take it back now, y'all.
So the photoelectric effect was sending photons at a metal to get moving electrons. And now we're going to be trying to produce photons by hitting a metal with moving electrons. So it's just kind of the reverse of the photoelectric effect. And overall, this is focusing on the same idea. The energy comes in packets or bundles of these quantized amounts, and it's going to take a certain amount of threshold energy to create these photons or these packages of light. So I kind of like to think of it like this. So here we have this personified light bulb, and he's going to be making photons. And he's got his diagrams, blueprints here for making a photon, and it requires a certain amount of energy. So if electrons are coming in like this, we see the electron coming in, and it's not moving with enough energy, he said, that's not good enough. I can't make a photon with that. We have one coming a little bit faster, still not good enough to make a photon. But then if one comes in with enough energy like this, that's enough for him to build a photon, and he's going to send a photon from this light bulb. So hopefully that animation gets across the idea that we need enough starting energy to make that photon. If the photon needs this many joules of energy, the electron needs to be moving with at least that amount so that we can create that photon. So looking at the equations, we use these two for the photoelectric effect. And this said that the electron will have this much energy, either represented by EK or QV. We could use both of those formulas. That's the energy of the electron. It was based off the energy of the photon, that was HF, minus the work function, which is how much energy it takes to liberate that electron. We're going to be focusing right there on the energy of the photon. So we need to know if we have enough energy to make that photon. So we're going to look at this equation here, where again, this HF is the energy of the photon we're going to be producing. And the QV, well, the Q, that's the charge of that electron coming in. And the volts is going to be how much we have to turn up the volts on our circuit to make it so we can make a photon of that much energy, HF. Now, when we're making photons, it's common to look at the wavelength instead of the frequency. And we saw these conversions in a lot of our practice questions where we just had to use the universal wave equation to convert frequency to wavelength. So I'm just going to put those two together, where we're not going to deal with them separately. We're just going to put that into one equation. So to solve for frequency here, I would get C over lambda is equal to frequency. I know that looks like an E. Let's make that more like a C. And now we can plug in for F this into that equation. So it'll be H times C over wavelength, which is what we see right here. I'll clear those pen markings and we can see it a bit more clearly. That's going to be the formula we're going to use in this lesson. And just a reminder that this is saying QV is the energy of the electron in the circuit, and HC over lambda is the energy of the photon. We need enough energy in the electron to make that photon. So that means if you're controlling the voltage on a circuit and you put it on just a tiny bit and you get it hooked up to this LED light bulb, the light bulb's not going to turn on. There's not enough energy to make light there. But as you start turning up, it's still not going to be on for a little while. But once you hit that threshold voltage, enough energy is in those electrons to make photons or make that light, and then it's going to turn on. So we can see that in this example here. It says if an LED first turns on when a minimum voltage of 2.70 volts is applied, what is the wavelength and color of the light produced? So we'll start with our equation from the last slide. QV is equal to HC over lambda. We're trying to rearrange for wavelength because that's what it's asking for in the question. So I'm going to multiply it up to this side, divide QV down to the other side, and get lambda is equal to HC over QV. So I'm going to plug in Planck's constant here. I'm going to use the one using joules, 6.63 times 10 to the negative 34 joule seconds. Speed of light is 3.0 times 10 to the 8 meters per second. The charge on the electron, 1.6 times 10 to the negative 19 coulombs, and the volts, 2.7 volts. Now I'm just looking to make sure that these units work out. First on the top, I can see that I have seconds and per second, which is going to be canceling out. I have coulombs and then volts, and volts is the same as joules per coulomb. So if I have coulombs and then per coulomb, I can cancel those two out, and then I'm left with joules on the top and joules on the bottom, so those cancel, and I'm left with an answer in meters, which is going to work out because that's what I want for wavelength. And when you plug all that in, you should get 4.60 times 10 to the negative 7. It's common to put this into nanometers, so that would be 460 nanometers for our wavelength. Okay, so that's it for today's video. I hope that helped you to understand how we can produce photons from a light bulb. Make sure you give those practice questions a try. Thank you so much for watching, and I will see you in the next video.